Here we go over tests for independence and for homogeneity of proportions. It sounds a little complicated, but it's quite simple actually. Um, and first, let's get it into words first because that sounds very stupid. All right, not stupid. That sounds very abstract. Test for independence. Test for independence just means if two variables are related, we're just testing if one variable affects the other. And it's actually quite genius how they did it, how they figured it out. Which it's like, I don't know. I would have never figured that out. So we go to the purpose, and we want to check if two variables are related. Let's go the simple route. Happiness versus marital status. Happiness level versus marital status. Obviously, someone who's married is, on average, is likely going to be happier. But I don't know. Maybe you have to do the mean test for that one. But people fall into category like married plus very happy or married plus not very happy. So they test both. Um, and calculate the expected counts, assuming happiness and marital status are unrelated. That's the null hypothesis because you're assuming that. Use the chi-squared formula and compare it to the critical value or p-value. So I'm going to use a little bit of brain power here because it's a little hard to. I'm just reading it, right? I made these slides a while ago. So, um, let's assume they're married, and we'll do a bivariate data statistics, I guess. That's kind of what we're doing. Married plus happy. Let's say there's 10 people that are married plus happy. And we'll go really low, although that will definitely skew the proportions, I guess. So you always want to go high in data statistics, I guess. And then we'll have married plus non-happy. And as we know, that is probably highly unlikely. I guess if you're married, you'll be happier. So I guess we'll do 2 here. And then we'll do non-married plus happy. And I guess there's a little bit more. There'll be 5. And then we'll have non-married plus non-happy. And I guess that is also quite likely, but we'll just do 5 for the sake of it. And then let's have a distribution here. And this distribution is completely unrelated. Simply here, we're just measuring the amount of married, non-married, and yeah, that's only 2 because we're using bivariate data statistics here. Now, I don't know if that's the right word. I guess it's not. So we'll do married people, and we'll do 40 married people. And non-married, we'll do 10. And I don't know if this is the actual right proportion. I think 95% of people get married. I'm not sure. But the chance of getting married here using this is 40 out of 50, or 4 over 5. If you factor out the 10. Here we have 10 over 50. We could simplify this to 4 over 5, 10 over, or 1 over 5. So what does this tell us? So 4 out of 5 times someone will be married. Now let's go over to happy plus non-happy. And this is quite genius. I'm actually getting a little bit excited because I'm still amazed. We still go back to chapter 4 with independence, multiplication, and conditional probability. But we don't look at conditional probability here because that means we would use this right here, I believe. And we would use an overlap. But happy, let's assume there's 20 people. And I'm going this off my brain, so if the data looks skewed, I guess it is. And then we'll go 30. So the proportion is 2 over 5 people that are happy. And let me just mark this. So married, non-married, happy, and non-happy. And non-happy will be 3 over 5. Which I don't know if it's true if people are not more unhappy than happy nowadays. But let's calculate the proportion of married and happy. So the married and happy, assuming independent, so we're assuming these are independent, is 4 out of 5 times 2 over 5. And that will give us, let's do some simple algebra, it's going to be 8 over 25. I'm not sure if we can factor that even further, and I don't think so. Let's use my brain to calculate this, if I can. So if we factor 4 out, that'll be 2. I can't factor 4 out. If we factor, I don't know, we'll just keep it at 8 over 25. Anyways, this is the probability that someone will be married plus happy. But we come here and we see that if we add this up, we get 10 over 22. And these are relatively close. So here we're measuring if there's a huge difference. If there is a huge difference, then they are not independent. One is affecting the other. Because if you're married, you're more likely to be happy. In this case, we would use that simple logic there, which you can't use simple logic in statistics. You have to definitely kind of prove it, use data to support it. But the difference is that there's going to be a huge difference if they are related. So obviously someone who's married will likely be happier, using logic, of course. So this proportion might be a little bit higher. And by doing so, here it assumes that they are independent, meaning these are two independent events. Being married has no effect on being happy, and it should be that. So if there is a huge difference in there, it does mean that there is something causing that difference, which would be the dependence of happiness on marital status. Quite genius, actually. So here, let's use the conditional probability rule. The formula is basically, I just explained here how the formula for independence rule is derived, but we don't care about that. Then we just use the chi-squared formula, which, as we know, it's observed. And we'll use things here. I almost made the binomial expansion mistake again. So how many expectations we make a chi-squared distribution. And then what we do is after the chi-squared distributions, also we can simplify the expected value. Which is derived from the original formula. The expected value will give us how many people are happy. So we already have that over here. We have 10, 2, 5, and 5. And the formula here is just going to be category, other category divided by total trials. So the independence multiplication rule. No, sorry, this is not independence. And we can show this by algebraic manipulation, but I'm not going to do that unless you want me to. Kind of tired of proving things. But anyways, this formula should give you the expected value without having to calculate the probability first and then multiply it by the standards and multiply it by the number of trials, which is derived from the original formula, as I said here. Now sum together all the chi-square statistics, which are observed minus expected, squared divided by expected. Now the degrees of freedom is calculated by the formula rows minus 1, columns minus 1. I'm not sure how. Then you can calculate the critical value. And since now we have observed minus expected, we can just use the distribution again. And I love distributions. And they'll tell us if that is unlikely and if the alternate hypothesis is true. So here's the reasoning behind it, which is quite easy. I mean, I love reasoning. If you do so, it makes understanding quite a bit easier. So the difference, and I'm thinking here, if the chi-square score, or if the degrees of freedom score is higher than the critical value, it's unlikely. If it is, then that means there is a huge difference, and that means there is independence. And now we have to go to homogeneity of proportion, and there is dependence if they're far away, because that means the differences are huge. So null hypothesis is that proportions across groups are homogeneous. And the alternative hypothesis is that they are not the same. So we go over whether multiple groups share the same proportions. So let's say we have 2 or more groups and we look at one variable across those groups. So simple example, drugs, we go back to pharmaceuticals again. We test drugs A, B, and C. We check if each cause abdominal pain or if all groups have the same rate of outcome, meaning that if each drug doesn't really have a difference in abdominal pain, they work the same, and they have the same rate of outcome. So make a table of the counts. Calculate all the expected counts of all the groups, assuming all the groups have the same proportion, and it's the exact same formula using independent probability. Use the chi-square formula compared to critical value or p-value. If they're way off, one or more groups are different. Let's use some logic here. And let's go back to Sketchpad over here. Let's erase all this. So let's assume we have drug A, drug B, and drug C. So let's assume that we test the proportions equally and we get 10 out of 50, 10 out of 50, 10 out of 50. And here we check if each causes abdominal pain, make a table of the counts, And the expected count here is that after 50 trials, 10 people will have abdominal pain for A, B, and C. So I guess this is a homogeneous proportion, right? I mean, each one yields the same proportion. But we also have to see if it's the exact same formula using the independent probability. So it would basically be comparing it to abdominal pain again and seeing if each has an effect, then use the chi-square formula to calculate if it is unlikely. So it's simple logic again, but it is a little abstract to understand. So I would recommend explaining it to yourself a few times, like I'm doing so right now. So